doing some hogging cuts on the Atlas. We're making a drill fixture so that we can drill out the spots for the tow 3 transistors for our power supply, because we're having to make some modifications. So you can see this is where having the bed drive. The bed drive is going really slow right now. The bed drive, and then we have an upper motor. It's not quite a it's not quite modified like a Bridgeport, not yet anyway. But we have a tension drive, very basic speed control, a single sheave pulley, single adjustable sheave right now on this setup. I'm gonna have to disengage it in a second here, but so we're doing these hogging cuts, and I'm 3/16 deep, and it makes real easy work of those hogging cuts. Having both spindle and bed drive, having both the spindle and a bed drive available really makes life a lot easier with those hogging cuts. You see, maybe you can't see too well, but we're 3/16 deep in single pass. We don't have to do multiple passes because we have extra slow bed travel. So we can do extra slow bed travel, and then we can do deep cuts, so that slowing the bed down really facilitates those deep single pass cuts, and that's really a nice feature to have. So we got to get 2 inches wide for our power supply mountings for our tow 3s. So we need to do this is a tow 3 pattern. So we need to put a tow 3 pattern times 9 in this, and then this will get welded onto this with our TIG machine. So we'll have two paddles like that. This is 12, these will be 11. So we'll weld them up like that. Just like that. And then we're planning on going the tow 3 on this side, and then the socket on that side. And then, although I guess you could do it, you could do it the other way if you wanted to, but I think we're going to do the cans on this side, sockets on this side, and then we'll do a common bus. We'll do 2 common buses, and then they'll join here, and I still have to figure out where these can go. What will probably have to happen is we'll probably have to install this first. We'll probably have to install this as a component and then put the tow 3s in, which is going to be really hard for the underside. I don't even know how that's going to work. I don't even know if that's even possible. I don't think it's possible. But we shall see. With the power supply, we figured out that each transistor can roughly tolerate 3 amps worth of current, and that was a big oversight on my part. I don't know, because I'm still kind of learning this, but we figured that at worst case, each transistor would be passing 3 amps. So Or I guess I'll have to go back. Yeah, worst case. So we're going to have... God, what is it? Or is it more than 3 amps? Well, I'll have to go back and look at it. I don't remember. Anyway, we don't really want to exceed 3 amps. It's supposed to be about 2.9 maximum. So if we get too much current per transistor, what will happen is one will typically saturate, and when you go to try and turn off the base, there's so much current flowing that one will current hog, and then it'll stay on, and it'll be disruptive to the whole pass transistor array, and it'll still be passing current even though the rest of them are off, because there's subtle variations in semiconductor processing. Each one's a little different because you're talking at an atomic level. So we want to make sure that those subtle differences in the transistor are not magnified by one current hogging and another one not, because the one that current hogs is the one that'll get damaged. So we want to pass a minimum distributed load across all the transistors such that they turn on and turn off in unison, and there's no overstresses to a particular transistor causing a single failure. So that's where we're at right now. This is a major redesign, going from 6 or 7 to 18, which is a major change. Hopefully, I don't know if the thermodynamic load is the same joules per. It should be the same joules per second. Theoretically, at least in my mind, we're not going to be causing as much heat buildup because we're distributing the load through more devices that will handle more current instead of pushing the same joules per second through 7. So it's the same energy, but it's not the same resistance per unit volume in the semiconductor. We're using 18 transistors, so the resistivity in the junction is going to be much smaller compared to the 7 transistors, and therefore the I squared R effects should not be the same. So we'll have to see what our thermal loading is. I don't believe our thermal loading is going to be that bad. We already tested 11 transistors, and they did get somewhat warm to the touch, but not the 140 degrees Fahrenheit in 30 seconds that 7 transistors produced. So we'll have to see how things go. I don't really care about calculating it. It's kind of a waste of my time. Of course, I wasted time with the 7 transistors, but you learn through experimentation. So who cares? This is just for fun. So we are getting there.